In this video, I'm going to describe the idea of a limit. And what I've done is I've developed my own definition of a limit. This definition that you can see is something you wouldn't find on the internet or in a textbook, but this is how I view a limit. And I'm going to read it. It says a limit is a y value, that is the anticipated result of calculating y values from x values that get closer and closer to a particular x value. So a very important idea is a limit is a y value. When we substitute numbers into a function and we do the operations that are indicated, we get a single number. We get an output, an answer. That would be a y value. So limit is that it's on the output side of a t function with it that describes x values you plug in, y values you get answers. So it's a y value. All right, and we're going to substitute x values that get closer and closer to a particular x value. And so sometimes, in some cases, we have to anticipate what the result would be because in some limits, the ones that really are involved in calculus, most of the time, we can't actually substitute the x value we really want to substitute. So we have to substitute x values that are close to it, and then from there kind of anticipate or from that pattern figure out what the y value would be, which would be a limit. So we'll get into that. All right, but so that is my idea. That's my concept of a limit. Let me show you what I did dig up on the internet. I didn't do a lot of research, but I did a little bit. Okay, just to show you uh, what's been developed over time. So this first quote that you see goes like this. It says, when the value successfully attributed to a variable approach indefinitely to a fixed value in a manner so as to end by differing from it by as little as one wishes, this last is called the limit of all the others. So that's the idea of getting really close to a certain x value. All right, at the bottom quotation, that really is a formal definition, which you'll definitely see in a calculus book on limits. And it goes like this. The limit of fx as x approaches a equals, you see the capital L, if and only if for every epsilon greater than 0, there exists a delta greater than 0, so that if 0 is less than the absolute value of the difference between x and a, and that's less than delta, then the absolute value of the difference between f of x and the limit, that's less than epsilon. So this is used in epsilon delta problems, which when you go to college calculus class, you'll probably do epsilon delta limit problems, at least a few of them, and they're fun to do, and they help you understand what a limit is. But that's not what I'm going to do here. So that's the formal definitions. So let's show you how I think of a limit and develop my idea. Okay, so first of all, we have to be able to sure we can read it correctly. And you probably, when I read that formal definition, you saw how to read it. But if you look over here, I have on the right, I got limit. Okay, LIM. LIM is just an abbreviation for the word limit. Okay, then we have a function. Our function this time I'm talking about is x squared, and we're letting x approach something. Okay, in this instance, this problem, I'm having my x approach 2. So we would read it like this: the limit of x squared. Let's call it x squared because it is x squared. Limit of x squared as x approaches. That little arrow between the x and the 2, that stands for the word approaches. Okay, so approaches 2, but really it's not supposed to equal 2. Alright, limit of x squared as x approaches 2 is, and question mark. Alright, so let's do a few examples to show you what I'm talking about. So my first problem is what you already saw. Okay, I want to try to figure out, determine the limit of x squared as x approaches 2. And I graphed it on the right. So what I'm going to do is I'm going to do a t-chart. I'll pick x, that's going to be my input, and y equals x squared. Okay, it's going to be my output. Now I'm going to pick values for x that get closer and closer to 2, but I'm not going to actually pick 2. And I'll explain why at the end. Okay, so my first x I'm going to pick is 0. Then I'll pick 1. Alright, and then to get closer I'm going to pick 1 and 1/2. And I'll pick 1 and 3/4. And I'll pick 1 and 7/8. Okay, I won't pick 2. Alright, so when I plug in 0, substitute in 0 right there. 0 squared is 0. Okay, when I substitute in a positive 1, I do 1 squared, which is still 1. Alright, now when I want to plug in, substitute 1 and 1/2, I'm going to change that to improper fraction. That 1 times that 2 is 2, plus 1 is 3. So I'm going to convert 1 and 1/2 to 3 over 2. I'll square that, and I'll get 9 over 4. Okay, and just to help us understand maybe a little better, 9 over 4. 4 goes to 9 2 times and has a remainder of 1. Okay, so I'm going to convert that 9/4 to that mixed number, 2 and 1/4. Alright, 1 and 3/4. Okay, 1 and 3/4 is same as 7/4. When I square both those numbers, I get 49 over 16. 16 will go into 49 3 times and have a remainder of 1. So 49 over 16 is equal to 3 and 1/16. Okay, let's do 1 and 7/8. That becomes 15 over 8. I square the 15 and 8, and we get 225 over 64. Now 64 will go into 225 3 times. And 64 times 3 is 192. 3 times. And then the 225, take away the 192, that's 33. So the remainder is 33, and we have over 64, and that's really super close to 3.5. So I'll say that's about 3.5. Alright, so as I'm picking numbers that are less than 2, 0, 1, 1.5, 1 and 3/4, 1 and 7/8, I get closer and closer to that 2 without actually using 2. Okay, so I'm going to graph these points. Okay, so let's see, 0, 0 is down here at the bottom. Okay, alright, 1, 1 is right here. Then we go to 1 and 1/2. 1 and 1/2 is halfway between 1 and 2 on the, right there in the x-axis. Okay, so we go up to 2 and 1/4. So make my circle a little smaller, so a bit better. Okay, there's 2 and 1/4. Okay, 1 and 3/4 is even closer to 2 on the x-axis. It would be right about here. Okay, and that we get a 3 and 1/16, which is just barely above 3. So that's that point there. And 1 and 7/8 is really just in front of that 2, and our answer for that is really close to 3.5. So I'll put my last point right here. Okay, so as we go to the right from 0 to 1 to 1/2 to almost to 2, our y values are increasing. Remember, a limit is a y value. So far we see that's too high. Okay, our y values are getting up closer and closer to some number. Okay, alright, so let's pick list of numbers that are bigger than 2. I'm going to start out and pick 2 and 1/8. Then I'll pick 2 and 1/4. Then 2 1/2. Then I'm going to pick 3. Then I'll pick 4. Now I'm going to start at 4 because that's the furthest away from 2. Alright, when I plug in 4 into this function, 4 squared is 16. My y value is 16. I substitute in 3. 3 squared is 9. Answer is 9. Okay. Now 2 1/2, I'm going to change that to 5 over 2. When I square that, I get 25 over 4. And that's equals 6 1/4. Okay. Alright, 2 1/4 is equal to 9 over 4. Squaring both of those numbers, we get 81 over 16. 16 goes into 81 5 times. It has a remainder of 1. Okay, and one more. 2 1/8. 2 1/8 is 17 over 8. Squaring both those, we get 289 over 64. Okay. 64 will go into 289 4 times because we get 256, and 289 minus 256, that's 33. So we get 4 and 33 over 64. And again, we'll just call that really close to 4 1/2. 4 1/2. Okay, so let me graph those points. Okay, 4 and 16 is way up here. Okay, 3 and 9 is right there. Then 2 1/2, and 2 1/2 is 6 1/4. 6, it's about there. And we do 2 1/4. We get 5 1/16, just barely above 5 on the y-axis. Okay, and finally 2 1/8 is just to the right of that 2 on the x-axis. 4 1/2. Okay, so what are these points doing? Okay, well, we can see these points, they're going down to hit some value, right? So the y values are approaching something. Okay, you probably can see what it is. From above, the y values are coming down, and below, the points are going up. But we'll not talk about that yet. But wherever they would meet, that would be the limit. That'd be the anticipated result. Let's try another one. Okay, this time the function is the square root of x, and I've graphed it again. Now this time, we're just going to use whole numbers. Okay, so here's my x, my y. I'm doing a little t-chart. Okay, my x value is below this. Oh, I also changed what I'm approaching. I'm going to approach 4 this time. So I have to pick numbers that are getting close to 4. So I'm going to pick a 0 and a 1 and a 2 and a 3. I'm not going to pick 3 1/2 this time. Alright, when I plug in 0, the square root of 0 is 0. Plugged in 0, got an answer of 0. When you plug in now 1, we get an answer of 1. Alright, when we plug in 2, we get a square root of 2. And the square root of 2, of course, is an irrational number, but it's approximately about 1.414. Of course, it has infinitely many digits, infinitely many places behind that, but that's close enough for us, graphing purposes. Okay, and let's do square root of 3. Square root of 3 is about 1.732. Okay, so graphing these 4 points, we have a point at 0 0. We have a point at 1 1. We go to 2, we just be just just below halfway, really close. Alright, and when we get to 3, it would be about 1 3/4, so pretty close to 2. So what's happening with the grade points? Okay, they're going up, and they're getting close to something. What they're getting close to is going to be the limit. Okay, alright, let's pick some numbers that are bigger than 4. Let's pick 5, 6, 7, and 8. Let's do the one the furthest from 8. Square root of 8 is about 2.8. Okay, so I put a 2.8. Alright, the square root of 7 is about 2.6. The square root of 6 is about 2.4. And the square root of 5 is actually about 2.2. Okay, alright, and let me put approximately there so we don't want anybody to think these are exact answer. These squiggle lines, these mean approximately equal to. Okay, so let's graph those points. At 8, we're really close to 3. Okay, at 7, we come down to just over half. At 6, we're at about 2.4. And at 5, we're at about 2.2. So what's happening with the brown dots? Okay, they're going down, and they're going down to, they're trying to reach their value is approaching something. The Y value is approaching something. Okay, and you can also see it from the chart. Okay, from what are these numbers? The 0 to 1. Okay, they're getting higher, but they're getting closer and closer to some number. Okay, and of course these numbers down here, 2.8, they're getting lower and lower. They're approaching some number. Wherever they would actually meet, they kind of meet somewhere in the middle. That'd be our limit. Whatever that answer would be, that'd be our limit. Okay, you can probably see what it'd probably be. Okay, let's try a couple more examples. Alright, now this time I just have a function of a line. 2x plus 3. Okay, alright, we change what we're approaching. We're approaching 1 this time. So x and y. So let's pick some numbers that are smaller than 1 to the left of it on the number line. So I'm going to actually pick a -1, which we can select negative numbers. I'll pick 0, and I'll pick a fraction again. Let's pick a half. We don't want to get all the way to 1. Alright, so we're going to plug in. We're going to plug in a -1 here for x. 2 times a -1 is a -2. When we add 3, you get a +1. Okay? Next time we substitute in a 0. 2 times 0 is 0. 0 plus 3, well, that's a 3. Alright, and we'll do 2 times a half. Substitute a half. 2 times a half, that equals 1. Then we add that 3, we get a 4. Okay, so let's graph those 3 points. -1, 1 is right here. Okay, alright, 0, 3, which is also y-intercept. I put a point there. And when I go to just a positive a half, I'd be right here exactly halfway between 0 and 1, and I'll go up to 4. Okay, so what are these 3 gray dots going? Where are they going? They're going up to something. Okay, wherever they go up, that's where our limit will be. Alright, let's pick 3 numbers that are larger than 1. Let's pick 1 and 1/2. Let's pick 2, and let's pick 3. Let's start with 3 first. Okay, we're going to substitute 3. 2 times 3, that's a 6. 6 plus 3, that's a 9. Okay, alright, we'll substitute in 2. Okay, 2 times 2 is 4, plus 3, that answer is a 7. And then we're going to substitute 1 and 1/2. Okay, again, we'll change 1 and 1/2 to improper. 1 times 2 is 2, plus 1 is 3. 1 1/2 same as 3 halves, so we're going to substitute in 3 halves. So that 2 times that 3 halves is 6 over 2, which is 3. Or you can cancel out the 2's and just say 3 at the start. But then adding that another 3, you're going to get a 6. Okay? So let's graph these 3 dots. Starting, let's see, 3, 9. It's way up here. Okay. 2, 7 is right here. And then 1 1/2. It's halfway between 1 and 2. Right there. And when we graph it, it's going to be at 6. Okay. So there's a pattern going on here. Those brown dots are getting lower and lower. Okay. Where is it going down to? Okay. So the brown dots, they're going lower and lower. And the gray dots, they were going higher and higher. Okay. So where they meet, where you think they would meet at, that would be the limit. Okay. The limit is a y value. All right. I have one more example. Okay, and that's a trig function, and this will work with any kind of function. Other functions that I'm not using, exponential function, logarithmic functions, any kind of function you can imagine. So let's try a log function. A trig function, sine of x. And this time we're going to pick numbers that are getting closer and closer to pi over 2. Now I changed my grid a little bit. Okay, you can see that's 0, that's a 0. This 1.57 that you see right there, that really represents pi over 2. Okay, that's really close to what pi over 2. Of course, pi over 2 is an irrational number, but that's close enough for graphing purposes. The 3.14, that's going to represent our pi. The 4.71 represents 3 pi over 2. And the 6.28, that's 2 pi. Okay, and on the y-axis I went up 0.5, a half a block, then 1. So it's not really in scale. Okay, but you see a nice sine graph. Okay, so we're going to approach pi over 2. We're going to approach this number right there, pi over 2 on the x-axis. So I'm going to pick numbers that are smaller than pi over 2. Okay, the first number I'm going to pick is 0. And then I'll pick pi over 4, which is exactly halfway between 0 and pi over 2. Then I'm going to pick pi over 3. Okay, so if you recall your unit circle values, you can do this really easy. When you plug in 0, of course you see that's 0. Of course you use a calculator on that. When you do pi over 4, okay, that value would be square root of 2 over 2. And since square root of 2 is about 1.414, we're going to get about 0.707. Okay, close enough. Okay, pi over 3, the sine of pi over 3 is actually square root of 3 over 2. And square root of 3 is about 1.732. We divide that by 2, we get about 0.866. Okay, so let's graph those 3 points. 0, 0 would be right here. Okay, pi over 4 is exactly halfway between 0 and pi over 2, so I go up to about 0.7. So straight up from that blue X, about 0.7, so it's about 3/4 of the way up, about right there. And then now pi over 3 is between pi over 2 and between pi over 4 and pi over 2. It's a little closer to the pi over 4. That was a pi over 4. Okay, and now we're talking about pi over 3. A little bit close to the pi over 4. Okay, we got an answer of 0.86, pretty close to 0.9. So, all right, so it's kind of about there. Okay, so what's happening with these gray dots? They're going up. They're, they're going up to some y value. Okay, let me make that a little shorter. Okay, want some y value up there. Okay, you could probably figure out what it is, but let's say we don't know yet. Okay, so I'll pick 3 more points that are bigger than pi over 2, 2 pi over 3, 2 pi over 3, 3 pi over 4, and pi. Okay, well, 2 pi over 3, these are going to be, these are, oops, I made the, I connected the wrong ones. These two have the same value. Okay, it'll be about 0.866 again. All right, the 3 pi over 4, that's going to match the pi over 4 in value. So it's about 0.707 again. And sine of pi, well, that's 0. Okay, so starting at pi, way over here. All right, we got a point of 0. Then at 3 pi over 4, 3 pi over 4 is exactly halfway between pi over 2 and pi. We get a y value of 0.7, which is about up there. Okay, and 2 pi over 3 between pi over 2 and 3 pi over 4. Okay, so somewhere in there, closer to 3 pi over 4, 2 pi over 3, and about 0.8. Okay, so what are the brown dots doing? Well, they're going up too also. Okay, but they're going up slower and slower, so they're heading for some y value. All right. Now, of course, you can probably see what they're heading for. Okay, um, you can see that it's heading for an answer of 1, and that limit for this is 1. Okay, okay, that's where it's heading for. That's the anticipated result. That's what the limit's going to be. Okay, let's go back and finish these other ones. Okay, all right. You can probably see what we're heading for here. At the first problem we did, we got 2 answers. We got 3.5. We got 4.5. Okay, well, it's going to be in between there somewhere, and we probably think it's 4. The answer actually is 4. Okay, and you say, wow, I could have just done like I did a regular function. Okay, put this 2 right there where the x is, 2 squared, and that's a 4. Why are we doing all this charting and all this stuff? Okay, well, you'll see hopefully really soon. Okay, all right, this one here, the square root of x, what do you think the limit is? So far we have a 1.732. You see that right here. And 2.2, the limit somewhere in between there. It looks like it might be, we anticipate it's probably 2. Okay, and the actual answer is 2. The limit is 2. And again, you can substitute that 4 in there. Square root of 4 is 2. So again, why are we doing all this when all we had to do was substitute our number in? Alright, this one here, the line 2x plus 3, boy, it looks like these 2 arrows are heading for that 5 right there. Okay, oh my goodness, can it be 5? Is the limit 5? Yeah, the limit is 5. The limit is 5. Okay, because when we plug in that one that we're approaching, that one goes right there. 2 times 1 plus 3, we get our limit to be 5. Alright, so in some cases we can actually substitute our number in and find the limit that way. But here's a case where it's not going to work. Okay, why not? Okay, well, let's just substitute in 2. Well, first of all, I have 2 places for x, so I have to make sure substitute 2 in both places. So substitute 2 there and 2 there. Alright, in the numerator I get 2 squared. 2 squared is a 4. And I still have that minus 4 behind it. In the denominator I have a 2 minus 2. Well, 4 minus 4 is 0, and 2 minus 2 is 0. Now, when you try to do 0 divided by 0 on your calculator, you're not, your calculator is just going to say error, we can't do it, okay? And we don't do that in math. We don't divide 0 by 0 because we can't predict what the result would be. So, all right, that didn't work in this case. So we have to find what's the anticipated result. So let's pick some numbers. We're approaching 2, okay? So let's pick some numbers that are getting close to 2. Okay, so I'll pick 0, I'll pick 1, I'll pick 1 and 1 half. Okay. Alright, so when we substitute 0, remember we have to put in both places. 0 here and 0 here. 0 squared is 0. So we have 0 minus 4 in the numerator. 0 minus 2. So we have a negative 4 over negative 2, and that equals 2. Okay? Now let's substitute 1. Okay? Alright, let's substitute 1. 1. We have 1 squared, which is 1, minus 4. 1 minus 2. We get a negative 3 over negative 1. That answer is a 3. Okay? Let's do 1 and 1 half. 1 and 1 half is 3 over 2. Okay, so we're going to have to square 3 over 2 first. That's a 9 over 4. Okay, I'm going to subtract 4. And I'll substitute a 3 over 2 in the denominator. Okay? Alright, so the easiest way to do this is change that 4 to 16 over 4. So I have the same denominator. Same thing with the denominator. 3 over 2. I'll change that 1 to 2 over 2. So now I have 7 over 4 divided by 1 half. 7 and 4 times, excuse me, gotta flip the bottom. 7 over 4 times 2 over 1. Okay. 14 over 4, 7 over 2, 3 and a half. Whew. Okay, 3 and a half. Alright, let's graph these 3 points. 0, 2 will be here. 1, 3 will be here. 1 and 1 half, 3 and a half. Okay. Alright. So these 3 gray dots are going up and they're getting close to something. Okay, let's pick 3 more points. Okay, let's pick 2 and a half. And then 3 and then 4. Let's start with 4. Okay, we have 4 squared minus 4 over 4 minus 2. That would be 16 minus 4 over 2, which is 12 over 2, which is 6. Okay? Alright, let's substitute 3. 3 squared is a 9. 9 minus 4 over 3 minus 2. We get a 5 over 1, which is 5. Okay, output is 5. Alright, let's do 2 and a half. 2 and a half is 5 over 2. Okay. So when we square 5 over 2, we get 25 over 4. 5 over 2 minus 2. Okay. 25 over 4 minus 16 over 4. Now I'm going to change the 5 over 2 to 10 over 4. Okay. And the 2 would be 8 over 4. Okay. 25 minus 16 is 9 over 4. And 10 over 4 minus 8 over 4 is 2 over 4. Cancel out the 4s. I get 9 over 2, 4 and a half. Okay. Alright. Graphing these 3 points, 4, 6. 4, 6 is way up here. And then we do 3, 5. And then 2 and a half, 4 and a half. Okay. So the brown dots, they're coming down. And they're heading for some number. but we can't actually substitute um, the answer in. We can't substitute a 2 in there. But what's the trend? Looks like we're heading for a 4. Okay? And that will be the answer because you can see it's anticipated because we couldn't really plug in the 2 in this case. But we see by substituting in that we get closer and closer to 4. Okay? So limit is 4. Okay? Now, do we have to do all this stuff to find a limit like that? No. So the next video I'm going to do, we're going to work on techniques where we don't have to do all this graphing and calculate. All right, so you probably already see an idea that when we do a limit, looking at this limit, we see actually the numerator can be factored. Okay, so I'm going to factor that x squared minus 4. We're going to say that's x minus 2 and x plus 2. Okay, and the denominator we just say that, well, I see that's an x minus 2. And we'll see when we factor the numerator that the x minus 2 will cancel. So what we can say that this limit is equal to the limit of just an x plus 2. Okay, and now I can actually put that 2 in that for x. Okay, substitute that 2 in there and get our answer of 4. And now, and graphically, that'll just close up that open dot right there, because that's what the issue was. We had that open dot in there. We couldn't actually substitute 2 in because we had an open dot there. But the y values are getting closer and closer to that 4 from one side and from another side. So that 4 is the limit because that's the anticipated result. So hopefully that gives you an idea of what a limit is. I try to reassure you, we're not going to be doing tables and charts for limits anymore. See you in the next video.